start that. I'll talk about the stuff that you have. I'm going to help you with some AP format equations so I can show you kind of the ones I need you to focus on. And we'll kind of bring it all together. And then I will be checking as we're working on some things, some of your organizations we have. So we are looking at 2011B, I believe. So it should be the second problem on 1416, is that correct? Correct. So we did the first one. I'm going to do the second one as well. Then you just have to do the last two. So that's not bad. In a 3-chapter section, you only have to do 2 problems. Not bad. Here we go. Answer the following questions about the solubility and reactions of the ionic compounds MOH2 and MCO3, where M represents an unidentified metal. Dun, dun, dun. So first, A, identify the charge of M ion. So just based on what they have there, you should know what the charge is. What's the charge of that M? 2 plus, correct? Should be. When you look at the OH, it crisscrosses, and then the CO3, there's nothing. Carbonate is 2 minus. The OH one is the more telling of the two, correct? Because of the fact that there's a parenthesis there. So plus 2. I don't think you should be surprised that that's just a point. Okay. All right. Letter B. At 25 degrees, the saturated solution of MOH2 has a pH of 9.15. Calculate, so I and double I, triple I. Love them. I, calculate the molar concentration of OH minus in the saturated solution. Reminder, whenever you're given anything about pH, it can tell us H plus or OH minus. So what is the first thing, though, I need to think? There's 2 ways you can always do this in pH problems. But what's your first thought? What's the issue? It's not a direct answer. It's in pH, and I have OH, right? So either I need to get into OH or get them in the same size, right? I need to get them both in the H pluses or OH minus kinds of terms. So I guess hopefully I'm not sure if you're thinking this direction, but if I want OH minus and I have pH, I probably need POH. Right? I probably need POH first. So I'm going to take 14 minus 9.15 first. And then, we did this yesterday. What do I do after that? Times by negative log. 10 to the negative POH, right? Because I already have pH. So I'll just write it like this so you'd be good to go. Whoops, I'm sorry. And I'm surprised. I don't know why. I thought that was going to be 2. I thought it would be 1 point identifying that you needed to put it in OH. And again, I have it up here as well, so hopefully. There's only a point. But that was just I, which I did not write. Double I. Again, I, double I, triple I, they link to each other, so you're probably going to have to use them. It says, double I, write the solubility product constant expression for MOH2. This, you will always have problems with because it's just a little different. So when you're doing this, it says solubility product constant. So when I talk about equilibrium constants, I have all sorts of letters. What is this one? K, SP, solubility product. So your mind needs to go to the idea that you take a compound and you dissolve it, okay? It doesn't say it. I'm going to draw it up here, though. This is where everyone makes mistakes. this is a solid, it breaks up into its ions. Like that. Like that's the balanced equation. It always, well, how do I know that it doesn't start as ions and goes as a solid? Because it's a solubility product. How much is going to dissolve? So it goes, like you drop the salt into water, how much is going to break off? And I don't think that's definitely an easy connection all the time, considering all the other kinds of equations that we've dealt with. Once you see that, though, I'm not writing states of matter there because if it ever has a charge, that has to be AQ. So I'll give you a second if you haven't done it yet. Hopefully you can get that. You shouldn't have all of those there. There should only be a few. And this is only a point. In mind, there's only one equilibrium expression that would not be in brackets. And that's P. Everything else has brackets. So that's what it should look like. M2 plus times OH minus squared because of that 2. Right, there's 2 OHs. Okay? All right. Sorry. Triple I, calculate the value of the solubility product constant KSP. Okay. So it's asking me to solve for this. Keep trying to just get you into the mindsets of what we need to be able to use. If I need to solve for KSP, that means I need everything else. I need both these other things. I need M2 plus and I need OH minus already. So to me, if I'm ever solving for anything in equilibrium expression, I want to at least start with, and I'll draw it way over here, with an icebox, even if I don't need it all. Okay? So maybe you're like, I don't need one. That's great. You're fantastic. This is more for me as organizational purposes. So, why am I doing this? Because I want to make sure I'm understanding what I have. Okay, let's go back for a second. And what did I do in I? Is I found a concentration of OH minus. Hey, that's in my green equation on the bottom there. pH. If I was doing an icebox, where is that? I, C, or E? The values from pH are always in E, right? It's where the reaction ends up. That is vital. So right away, bam, oh, that means that this, if I'm doing ICE, the bottom part is 1.4 times 10 to the negative fifth. Okay, why do I set this in an icebox? Because you could easily flip this. Start working the icebox. I know that I initially start, here, I'll even do this in a different color. I initially start at 0, okay? And then I put in my x's. Let the simple math reveal itself. Because of that, what is the result of the concentration of my M? Is it doubled or is it halved? It's halved. A lot of you probably would have doubled it because you would have went too fast. But it's halved. So it would be 7 times 10 to the negative 6. Yep. Or it would be 0.7 times 10 to the negative fifth still. But you don't write it like that. It just looks weird. So then what do I do with that? Anybody, what do I do with that? Plug it into my KSP now, right? If I know numbers, if I know every number that I need on my E line, I can plug it all into my K expression. So that's the key to this. And I just don't know why you wouldn't want to do an icebox. How hard is that? That's not difficult. It's just addition and subtraction, basically. But it takes a lot of knowledge to be able to say, I'm going to bring it down here, I'm going to have that equilibrium, so on and so forth. Anybody else get something like that? How many do you think that's worth? Probably, it's probably 2. If you're like 1, that's a big one. Let me show you what you have. You have 1 point earned for this relationship. So understanding that you got both those. Now, they did it in a very different way. They did it in a much more, I think, complicated and confusing way. Use ice boxes whenever doing any equilibrium. And then, as always, there's always a point for the answer. Okay. All right, we go to C. So that problem's kicking your butt, as we talked about. It's not that you can't reset. Yeah, Morgan. It is. Yeah. Okay, so every KSP is going to be really tiny because what they're doing is things that aren't very soluble. So they're very small numbers. So what it's saying is that it doesn't create, like, it's small, so it doesn't go very far to the right. It lies to the left. So only a little bit of it's going to dissolve. So the bigger the KSP, the more soluble something is, because the bigger the K, in general, the more to the right I am. So all KSPs are about solid versus ions. So the more I'm to the right, the more that can dissolve. You're never going to have a KSP for like a nitrate, because that's like saying having a K for a strong acid. It's going to the right. A nitrate's going to break apart. I don't even know what a K would be, like a sodium nitrate. That would be alkali metal and nitrate. It would blow up the calculator. Okay, let's keep moving. Letter C. So as I keep saying, though, if it you have to reset, so be it. It says for the metal carbonate MCO3, the value of the solubility product constant KSP is 7.4 times 10 to the negative 14. On the basis of this information, it results in part B, which compound, the hydroxide of the carbonate, has a great, oh, Morgan, what a great segue. Greater molar solubility in water. Justify your answer with a calculation. Interesting. Subtract the two? Are you sure? That's okay. You should probably recheck this one. Sorry, just a second. Feeling like this shouldn't be that complicated. I'm glad because like 4 people come in, we completely get derailed. That's awesome, by the way. Tyler. Talk to him every day. Okay, so in general, which one has the greater molar solubility? You just look at the answers. I mean the values of K.
Mr. Gussie, there's any more chapter stuff.
I don't know how that's possible. Anybody take extras? Here, I'll give you mine. Which one has the greater molar solubility based on just the values of K? The carbonate? Not. The carbonate has a greater solubility. I guess I'm just not reading this correctly. All right, what we need to do is we actually have to have a value. They're wanting us to find a value. So molar solubility is what would be the actual molarity of a compound, the maximum, the saturated molarity of that compound, not of an ion, of an actual compound. Okay? So what that always is, by the way, molar solubility, I'm going to write this before I even do the problem. That is a saturated molarity. That always will equal X. X is always like the 1 to 1. So whatever you find for X, that is your molar solubility. So we already know the molar solubility of the first one. Do I know that? Well, I have it right above. So the molar solubility of MOH2 is what? 7 times 10 to the negative 6? Because that was X. If you're like, I don't get it. This goes way back to the idea of this. If I tell you I have CaCl2, and I tell you that the ions of Cl minus is 4 molar, what's the actual molarity of CaCl2 though? It's only 2 molar, because it doubles. Each ion carries those molarities. So Ca would have 2 molar, Cl would have 2 molar, and Cl would have 2 molar. Cl would be 4 molar because it's 2 each. So this whole thing would have a molar solubility of 2 molar. So that's where the X kind of comes into play. So what we need to do is find the other one. We'll figure it out. All right, so we need to quickly go through this one. This is how we do it. I need to just find X. So, check it out. If I have KSP and it equals M2 plus times CO3 2 minus. By the way, if you're like, I don't know where I'm going with any of this. If you're given a K, then you need to be able to find the concentration. If you're given concentrations, then you find your K. It's always one or the other. So the fact that they gave us, I gotta look up the value here, they gave us the KSP expression, what is that going to equal? It's going to be X times X. Why? Those are both 1 to 1. If you put this all into an icebox right here above, it'd be 0, right? 0 plus X, X plus X, X. Oh, it's just X squared. So X is going to equal the square root of that. And that's it. So which one has a greater molar solubility? The hydroxide or the carbonate? The hydroxide because it has a larger number. Bless you. Okay. So that was tricky. 1 point is earned for this, and 1 point is earned for saying the answer. Molar solubility always equals X. All right, finishing up. These last ones are short, and then we're going to get into some free energy stuff, which is very familiar to you, a little bit of electrochem. I'll talk about the things that you have. I'll talk a little bit about some equations. And what's not. Letter D. So MCO3 decomposes at high temperatures as shown by the equation represented below. So they give you an equation. A sample of MCO3 is placed in a previously evacuated container heated to 423 and allowed to come to equilibrium. Some solid MCO3 remains in the container. The value of Kp for the reaction at 423 is 0.0012. Okay, don't make preconceived ideas. Wow, there's a lot of information. It gives me 3 I's. They're going to build it up for me. Letter I. Write the equilibrium constant expression for Kp. I just have to write the Kp expression. That does not mean numbers. So look at that equation. What am I going to have in there? CO2. Just the CO2. Remember, Kp's, P's are pressures. It only deals with gases. You're not even going to have AQ. They won't relate it to that. You got to make sure you write it correctly. If you put a bracket, it's wrong. So did you put a bracket? If you did, you messed that up. Don't put a bracket. Double I. Again, just stay with this. Don't set yourself up for failure by thinking you don't understand the problem when you haven't even read them. Determine the pressure of CO2 in the container at equilibrium. This is an equilibrium expression, right? So is it not 0.0012 ATM? And if you're like, it can't be that easy, I'm showing you right now that it can be that easy sometimes. you're seeing what I'm saying, by the way. If you're like, you're laughing like, oh my god, I hate that feeling when you're like, oh gosh. I don't see it. Afterwards, everybody's like, yeah, I didn't either. Oh, no. They equal the same, right? Equilibrium. Triple I, indicate whether, so all this information they gave us, almost none of it actually is going to be applied. Indicate whether the value of change in G for the reaction at 423 is positive, negative, or 0. Justify your answer. Okay, this is a good question. What are we dealing with right now? Before I said G, what did they give us? What's the biggest thing they gave us in this? What are we working with? They gave us pressure linking with a equilibrium, K, right? Okay. The minute you see that, you got to see the ties. They're asking about change in G, and they're giving me a K. So this has got to at least be on the thought that this could apply. Why am I saying that? Well, I'll show you where I'm going with that. So if I do that, and I put the K in to the equation, it applies, right? It will affect it. Now you're like, well, can I plug all those numbers in? Potentially. And you could probably get an answer. The problem is with this, well, it is a question mark. What does 0.0012 mean to that equation? And what I mean by that is this. What does 0.0012 mean for an equilibrium expression? Favors right or favors left? It doesn't? A K always tells us where it lies more, right? If it's greater than, right, because it's products over reactants, correct? And you're like, well, you only have a product. I'm aware. Doesn't matter. If I have a number greater than 1, doesn't it favor the products, right? I'm doing this. I can do this without calculations, what I'm trying to show you right now. And if it's less than 1, it'll favor the reactants, right? To be considered spontaneous, which way do I have to go? I have to go to the right. I have to go to the right. If it wasn't spontaneous, then it's like, oh, I'm just never going to move. I'm going to stay over here. But I'm spontaneously staying over here. No, I have to have the reaction move forward. So the very fact that K is less than 1 means what? Spontaneous or non-spontaneous? Let's say that first. Non-spon. So let's just write that. So because of that, is it just asking the sign of G? Yeah. Change in G would be positive. So no, I know, well, why did you write this and everything else? I'm just saying that there's a relationship there, so it does tie in. But in general, all you got to ask yourself, is it naturally going to the right? Is it actually occurring? That's only a point. And it's all said and done. Okay? So, hope that kind of makes sense. Does anybody have an extra chapter 17? I did make exactly the right amount. I will check. I can quickly go check the room. I can't hear you. All right, let's go. Here we go. Chapter 17. These don't take that long. The gas N2O4 decomposes to form the gas NO2, and it shows it to you. I predict the sign of change in H for the reaction. Justify your answer. All right. This is a really good question as a review because you don't have anything there. So let's just talk about what you see. What physically happened? You broke a bond, right? So what do you have to do to break bonds? Think about breaking a stick. Think about playing Red Rover, Red Rover. If you're going to break something, are you putting energy in or taking it out? I got to put energy in. So my change in H will be positive because it's gaining energy, right? Bonds are broken when NO2 molecules form from NO2O, N2O4 molecules. Energy must be absorbed. That's what I probably should have written to break bonds. So the reaction is endo, and the sign is positive. Double I. Predict the sign of change in S reaction. Talk amongst yourselves. What is that? These are easier than you think, and they're easy points if you understand it. G is free energy, S is entropy. So S is not, please understand this is what starts to happen. S is disorder or order. What does it mean? It's disorder. Be careful. People all of a sudden just, oh, it's order. Oh, no, it's about disorder. The actual phrase is disorder. So, positive or negative? Positive. I'm gaining disorder, right? I went from one molecule, this is simple as this. I went from one molecule to two. I'm gaining disorder. Okay? So it's definitely positive, and that's exactly what you can write. And I can't find it all of a sudden. Oh, there it is. You went from 1 mole of gas to 2 moles of gas, right? 1 point. B. On the diagrams below, best represents, one of the diagrams below best represents the relationship between G and temperature for the reaction given in part A. Assume that change in H and change in S are independent of temperature. What? Draw a circle around the correct graph. Explain why you chose that graph in terms of this. All right, they give this away. They give that away just a little bit in terms of that. So it's not about letter A. You're like, wait, it's about letter A. It doesn't refer to letter A. It doesn't refer to the reaction. It's saying in general, okay? In general, that's what it's saying. But you can just assume this. So if you just set certain numbers, as I'm gaining temperature, right? That's what this is saying. So as this T gets larger, what happens to this expression here? That'll get a larger expression, right? And then you're going to be subtracting it more and more, right? So mathematically, what does that do? What is it? The left, middle, or right? Oh, fail. Huh? The leftmost graph should be circled. A change H, S is positive. So as T increases, T change in S becomes a larger positive number. At higher temperatures, you are subtracting larger positive numbers from H to get G. So G decreases with temperature. Okay? I will say that again. This is the most important part of that because they're trying to push you to that T part. If change of S is positive, and that's why I'm hesitating because it's not referring to the first one, but yet they're saying that it's positive. But if something's driven and it's normally going to occur anyway, it's going to gain disorder. By increasing that temperature, that value is going to be getting a larger and larger positive value. And you got to just somehow, it's hard to describe a mathematical equation because it's like you feel it's already explained through the equation itself. So keep it simple, just get to the heart of it. Well, this is causing this part to be larger or smaller, and by subtracting or adding that, this is the result. That's how I would try to stay focused on it. You don't need to try to start explaining the chemistry behind a mathematical relationship. That's the relationship. So you can definitely talk about it. It's actually 2 points. And I'm not going to write it all. 1 point is earned for the correct selection, and then 1 point is earned for the explanation. You needed a little explanation. So you had to do it in terms of the equation. Okay? Moving on. Letter C. A reaction mixture of N2O4 and NO2 is at equilibrium. Okay, so we're at equilibrium. Sorry. Heat is added to the mixture while the mixture is maintained at constant pressure. I, CI. Explain why the concentration of N2O4 decreases. You do not need to know that beforehand. It's telling you it decreases. So it says heat is added to the mixture when the mixture is maintained at constant pressure. Explain why the concentration of NO4 decreases. So let me, because I don't have it in front of me again, let me reestablish what we're doing here. We have this going to that, right? So what it's saying in letter I, when I add heat, that decreases. Anybody want to explain to me? It only takes 1 second. What? Mason? So we don't say it that way. The energy is that you're on the right track. Your energy is on the left side, so we'd say this reaction is endothermic. So because it's endothermic, but actually that's more or less the answer. Because it's endothermic, adding energy or adding heat causes the reaction to drive to the right. That's what I would say. They say it this way. The reaction is endothermic. For endothermic reactions, increasing the temperature drives the reaction to the right. This increases the equilibrium concentration of NO2 and decreases it of N2O4. Please understand, if it ever starts talking about increases and decreases of amounts, you have to at least entertain the thought of the Chatelier's principle. And maybe they wouldn't say, oh, that's not what Chatelier is. It all falls under that. By putting energy here, you establish that, right? If you increase it, what always happens? It drives away from the addition, right? It goes towards the subtraction. So it's going to cause it to go this way. So because it was endo, it drives it to the right. I'm so glad, Mason, you're totally right. And I'm glad you said it the way you did, though, for everybody here. You cannot actually say energy's on the left. That's a trick we have. What you do is you act like you got it all down, and you're like, well, because it's endothermic, adding heat drives it to the right, which I always hate, because it's like, what? Like, everybody knows that. Not everybody knows that. Okay. 1 point. Double I, we're almost done. The value of KEQ at 25 degrees is that, 5 times 10 to the negative third. Will the value of KEQ at 100 be greater than, less than, or equal to? Please be careful. Talk with someone else. Do you think it's going to go up or down? So, by the way, what did I do? What's the original temp? Where does it even say that anywhere? Did it say it? I can't find it. Oh, there it is. All right, at double I, it says at 25 degrees. Sorry, I didn't see it. That's the K, and now it's at 100. So, be careful. Think about what that is. So, will K be larger or smaller? Yeah, sure. Sure you got enough there? For the whole roll? It wasn't even for you. What a good friend. Embarrassing, Ashley. What? You were born at 420? Because my son's birthday yesterday. He turned 9. That's actually the reason why we came home. So I've been here 9 years. We need babysitters, called parents, or grandparents. Okay, if I increase temp, what am I doing? That's what's important. You can't just be automatically, oh, temperature goes up or goes down, so it gets bigger or smaller. Because the temperature increases, do I go more products or more reactants? More products in this case. It's a double I. It's setting you up from a single I. So because I went this way, I'm going to make more of this, right, and less of this. So K increases. Wait, that's not the right word. Greater than. K would be greater than because, and this is what I'd write, because at 100 degrees, more products would be formed. Is it not? 1 point is earned for the correct choice, parentheses, no explanation required.
You got 33%.
Bogus question. I don't like that at all. I'm gonna hate the player and the game on that one.
Why not just?
That's ridiculous. I'm sorry. Sorry, AP board. You hear me? You're going through my desk right now. Using the value. Let's finish up. Using the value KEQ given in part CII, predict whether the value of change in H is expected to be greater than, less than, or equal to the value of T change in S. Explain. Okay. I want to finish this. So, guys, the fact that they talk about this and they talk about this, what are they pushing you towards? Okay, let's talk about that. So I can figure out this problem in the fact that they're trying to slowly break it down for me. What the question is predict whether the value of this is expected to be greater or less than this. Days left. Okay. So what don't I have? I don't have G, right? But I do have G. It says use the KEQ from at 25 degrees. So 25 degrees, what does that tell me about G? We already answered this once before. Is it positive or negative? K is less than or greater than 1? It is. Is it not less than 1? So that means it's not spontaneous. So this has to be positive. So, simply put, which one has, let's make sure we answer the question correctly, will H be greater than, less than, or equal to, well, it can't be equal to, because it'd be 0 then, right? Is this greater than, less, or greater than or less than that? Has to be greater to make that positive, correct? That's all this is. Like, that's just manipulating an equation. It has to be. This has to be a larger number than that to get a positive final number. But the key to this is because K was less than 1. So just understand that. If you don't know that part, you're done. Like that's the whole point. So because K was less than 1, you get 2 points. 1 point earned for the prediction, 1 point earned for an explanation. Literally, the explanation is, I'll just read it. KEQ at 25 degrees is less than 1, hence change of G must be positive. And in order for change of G to be positive, change of H must be greater than than T change in S. That's 2 points though, which I thought was pretty crazy. So this has to be greater, that's 1 point. And then just an explanation really kind of going off of this. Okay? One more. And we are actually on track then. Like we're not behind at all. Well, yeah, but I have stuff to talk about. It's a relative term. Last one, you're going to a Electrochem. Here we go. We'll see how far we get. I might have to cut this short and talk about it tomorrow only because I have to talk about and address a few things. Here we go. Let's please have transitions easier than this. In a lab experiment, PB and an unknown metal Q were immersed in solutions containing aqueous ions of unknown metals Q and X. The following reaction summarizes the observation. You got a bunch of stuff going on there. A. This really has nothing to do with Electrochem yet. A. On the basis of the reactions indicated above, arrange the 3 metals PB, Q, and X in order from least reactive to most reactive on the lines provided. So you can literally see, it's like a single replacement reactions. If you were going to make an activity series, which one seems to react the most and which one seems to react the least? So that's the key to this. So you got, what we're placing here is P, B, Q, and X. And you got to put them in order. So what do you think? And don't try to do it all at once. Can you figure out the least reactive? Can you figure out the most reactive? That's probably the first key. No, you got anything for me? Most, what's pushing you there? Yeah, good. And specifically, if you remember this, in an activity series, the thing by itself, you have the dancing couples, and I was talking about prom and everything. You got, I won't get into that now. You got the one by itself, then you got to get in the dancing couple. That one by itself has to be more active than the people that are dancing for it to get into the pairing. So because of the fact that it's by itself both times and it reacts, definitely PB is the most reactive. By doing that, I make life a little easier. All I got to do is figure out Q and X. I look at reaction 2 and it will actually tell me. So if the metal by itself can kick out the one as an ion, then it's more active than it. If it can't, it's not as active as it. So what is it saying? Who's the least reactive? It's Q, because Q can't kick out X. X is more active. X is already dancing. Q comes over. It's like, oh, Q, I'm not as active and as coordinated as you. So this is Q. This has to be X. Listen to this. Okay, we won't probably get through this whole problem, but we'll get as far as we can. I think this is genius on their part. 2 points are earned for the correctly ordered relationship. Okay, so you get 2 points, just point blank. But 1 point is earned for 2 different ways. You could then QPBX or XQPB. But if you just like wrote the same letter twice and then one other one, you wouldn't get any of the points. You have to have all 3 written. You know what I'm saying? Like sometimes like, well, I don't know which one, so I'm just going to, cut my losses to try to get something out of this. You'd have to commit to all 2 letters though. You can't just somehow write like XXPB. Or I can see a kid going PB, PB, PB. I got PB in one of the right spots. No. All right. 2 points. You got that order. And you got 1 point if you just flipped one of them. So if you got one of them in the right spot, just flip the other 2, you actually get 1 of the points. So not bad. All right, here we go. So there's a lot written here. Diagram below shows an electrochemical cell that is constructed. A lot of this is just information. You got PbNO3, you got XNO3, cell bridge containing KNO3. When the electrodes are connected to an external circuit containing a switch, which is open. So this is an open switch, by the way, meaning that it's not on yet, like a light switch. I turn on the switch, then everything's connected. When a voltmeter is connected to the circuit, as shown, the reading is 0.47. By the way, the minute that voltmeter's there, this is a spontaneous reaction. That means it's naturally occurring. When the switch is closed, electrons flow through the switch from PB towards X. The minute I see that, I am drawing that because that tells me everything. I am understanding flow. You have to understand where the electrons are going. That is so vital. They tell you that right there. Electrons flow through the switch from PB towards X. And you're like, oh, it always goes from left to right. That doesn't need to be like that. Okay, let's just see how far. Again, I need to talk for a good 6 or 7 minutes yet, so we'll see a couple of these problems. B. Write the equation for the half reaction that occurs at the anode. All right, we're going to be practicing this a lot in the next week. But there's a cathode and an anode. You have to remember what happens there. You got oxidation and you got reduction. Does anybody know which one happens at which? Is what? That's right. N-ox. You remember this as an N-ox and a red cat. So anode, cathode. So the question says, write the half reaction that occurs at the anode. An anode means that I'm having oxidation. And we will be looking at this because this stuff, to be honest, is not that tricky. We just need to review a little bit, and we're going to get it right back. So what does oxidation mean? It means you gain charge. Well, here, oil rig. So oxidation involves losing electrons, but that means that the charge goes up as you lose electrons. So let's just look at what happens. Who is losing electrons? The electrons are flowing away from the PB, right? So you start at PB, okay? You don't need states of matter. If you lose electrons, they got to be on this side. It's just that simple. So what is the charge on PB? Look at the formula of a solution that they gave us earlier. It's a 2+. It says it right here. So where does the 2 plus go, on the left or the right? Think about this. I lose electrons. Right or left? It has to be right, and then there's one last thing that's not correct. 2 electrons. Unfortunately, I got to make an executive call here. So we will finish this one up later because I need to come around yet and check your organization as well. But I also want to talk, if you want to quickly get out your AP format, I want to show you how to do a couple things. The ending of your big packets that have the reactions on them. Okay, do this very quickly, please. AP format 1, circle 2 and 4. AP format 2, circle 1, 2, and 3. I'll say it again. AP format 1, circle 2 and 4. AP format 2, circle 1, 2, and 3. Now, I'm going to show you a couple things quickly here, but those are ones that I absolutely expect that you should be able to completely get right. So these other ones have a little bit of extra things, and I want you to attempt it with a little extra flair to it, but some of it might just be off-centered a little bit. So let me show you, let's do number 4 on AP format 1. And I got to still come around. It's going to get tight. As I'm doing this, if you can, unless it's already out, have whatever you're going to show me ready to go without making a big commotion about this. That'd be awesome. So it says magnesium turnings are added to a solution of iron 3 chloride. What you need to understand is that we're trying to do these in things called netionic equations, meaning that anything that's in solution are ions. So if they're called spectator ions, they don't stay in the equation. So we are only writing the active chemistry. So magnesium turnings are added to a solution of iron 3 chloride. Now, I'm not worried about all of the balancing yet. I'll balance that later. But this was a solid, and then I'm not writing AQ. Anything that has charges are AQ. So I'm driving that in. What kind of reaction does this look like? It's just a single replacement. Assume all these happen. None of, like, if you ever get an equation, unless if it asks and hints that does this happen or not, these are happening. So Mg is going to try to kick out Fe. So Fe will be kicked out. When they are kicked out, they're truly kicked out. So that means they are now a solid. Now Mg goes in to solution. Okay? Can I cross anything out? What can I cross out? Okay. So now I do need to balance that. Well, wait, all the atoms are balanced, but the charges are not. So I see 2s and 3s. So I got to make those 6s. So I do that, I do this, and do that, and do that. Now there's a follow-up question. There's always a follow-up question. It says, what is being reduced in this reaction? Justify your choice. Again, the whole point of this, guys, you will learn simply by working on these and using the answer keys. I'm shocked. And you know what? If you want to hide them, I'm amazed how many people are still just sitting in the commons, and when I walk by sometimes you have nothing out. That borderline almost offends me, in the fact that you are literally not doing anything, like, during the day. Like, I don't know what you're doing. And I need a rest. Okay, but I see that all the time. I'm shocked. You could be up and just doing a couple problems from time to time, or working with someone else or something. So, it surprises me. What is being reduced? What is being reduced? Reduced means that reduction involves gain. Oil rig. You're gaining electrons. Fe went from 3 plus to what charge? To 0. So the answer is Fe because it went from 3 plus to 0. It gained, if I had to answer this, gained what? How many? Gained 3 electrons. Okay, because I want to make sure this has value, I'm fine continually doing this. Next Monday, 1 and 2 will be due. Tuesday, 3 and 4 will be due. I didn't even talk about which ones 3 and 4 are vital, but they have purpose and value. I'm seeing that what we're doing in classes is taking a little extra time. I'm okay with that. So Monday. And if you've been working on it, great. You'll have other things that can take its place. Those are what's due. Lastly, 2 things I handed out. Blue sheet. I did not make this. And then I'm going to come around quickly and check. This is a little antiquated, meaning it's a little older. So not everything's perfect. Some of it may not be as stressed, but it is a nice reference. It's a all-in-one kind of thing. Please understand there are certain parts like, whoa, wait, what's that? But at certain points, like, oh, hey, this is all nice and organized. This is all my kinetics. This is all my equilibrium. This is all my molecular geometry. Use it as you will. But I always think it has some value to hand out. Well, definitely. Secondly, the big packet I handed out. I have been trying to be upfront about this. I have not emphasized multiple choice nearly as much. That is totally optional. It is a complete multiple choice test with not only the answers, but every explanation to all the answers and why. I would strongly suggest doing it. I really would. Oh, I can't do the whole thing. You don't have 90 minutes? Fine. Do half. Give yourself half the time and do half the problems. And then do the other half another half. Don't use a calculator. What I would suggest, the way I designed it, is rip off the top sheet. That's how I have it. So you rip off the front when you're ready and you fill in those bubbles. Okay? And you just go through the problem. So for some of you who are really annoyed by how I stapled it, it's only because you're going to rip off the top sheet and then it looks pretty normal for the staple. Again, the answers are at the end with every explanation of why. Okay? Please, you have three multiple choice. I will have that ready. I did not anticipate what was happening yesterday, so I don't have a spot. You will have to upload those. You got to get those uploaded. I will give that by, it says due tomorrow, so I will give it by like 6 o'clock if you need to get parent signatures later or so. I'll think about a good time for that. So it won't be necessarily by tonight, because I did say due by tomorrow. But am I wrong? Are there 3? Is it 8 and 10?
Then
Part 1 and part 2. Okay, 8 and 10, part 1 and part 2. So if you don't have those, you got to talk to me. Okay, about that. Lastly, I'm going to quick come around and try to sell me it if you're not sure that you feel like you've organized it or not. Okay. You got the paper clips going? I love it. Tabbing me. Tabbing it? Trouble with gas? Oh.
tweaking, bro. I'm tweaking.
Oh, get back to baseball.
pH is
Order